Welcome to my PhD proposal presentation on anonymous broadcast for blockchain transactions. When I started my PhD, the original idea was to create a cloud storage solution, something like Dropbox or the like, with commercial application, but with privacy as a foundational motivation. To realize such a project, we came to the conclusion that we need anonymous payments of some form and some form of storage contracts to actually ensure that a storage provider would store the files you would put in the cloud storage and that they would receive payment if they do so successfully. After a short discussion, we came to the conclusion that a blockchain would actually solve these problems or would provide a foundation to solve these problems. While most people probably know already about the blockchain, I'll still give a short and reductive overview of blockchains. Blockchain is a distributed data structure of storing more or less consistent data across multiple nodes in the network. This data is in block form as an aggregation of multiple smaller data sets, and there are links between the blocks of the blockchain, hence the name blockchain, that are used for integrity protection and enforcing a form of time in the distributed system. Such a block consists of multiple smaller data elements, usually called transactions. Such a transaction consists of some content description, what the transaction is about. In the most basic form of blockchain, this is usually a form of token transmission. So one person wants to transmit a token to someone in the possession of someone else. A signature that proves the sender is actually the owner of the original token, and some form of receiver. We already see there's a privacy problem in this situation, as this data is in a public data structure and stored on many nodes. We have lots of information distributed throughout the system. There are cryptographic means by which we can hide basically all elements of the system, like ring signatures to hide the originator of the data, one-time addresses that hide the recipient, and there are far more complex solutions to hide the actual content of the transaction. But once such a transaction is created in a privacy-preserving manner, it has to be distributed throughout the network so all participants can include them in the data structure. And when we do so, the simplest form of doing this is flood and prune dissemination, just sending it to all our neighbors. And relatively easily, we arrive at a new privacy problem. Because while we can no longer use the public data structure directly to de-anonymize participants, network participants that log the actual data on the network level can still receive information about the participants, like their IP address, and de-anonymize them in this way. In some way, this de-anonymization is even worse, as IP addresses can much more easily linked to real-world identities than cryptographic keys we had in the beginning. So how are other systems right now solving this problem? When we look at the most well-known system in blockchains, Bitcoin, they use a system of trying to detangle the topology and making it harder for people to just listen in on network connections and doing exactly that. When we look at one node in the Bitcoin network, for each outgoing connection, the node has a random distribution which they use to delay incoming messages by a random amount. So every time they send out an amount of messages, they will roll the dice and wait for this amount of seconds. And this is not hyperbole, they actually use seconds as their base unit on this. On average, they wait for 5 seconds, and at most they wait for 30 seconds. So during their waiting period, when transactions enter the node, they aggregate them, and once the waiting period is over, they send along this all received transactions along this outgoing edge. While this is more or less useful to hide the overall topology of Bitcoin, it can still be used. It's still not a powerful tool to prevent de-anonymization on the network for mid to slightly larger than small attackers that create enough nodes or connections within the network. The first approach most people take on privacy in such cases, and that's also used within the Bitcoin net because it is applicable there, are onion routing services such as Tor. Tor can also be used as a proxy service, so just hiding the TCP throughout the the TCP connection within a Tor tunnel, and around like 20% of people use this to connect to the Tor network. This has a few disadvantages and a few advantages. One of the biggest advantages is that it can be easily combined with regular protocols without much additional thought put into it. The negative part is it's not well designed for broadcasts, so if we just use Tor as a tunneling service, which is mostly the case for applications in blockchain networks, we are not possible to fight off attackers that have a good overview over the connections of many participants, which could be created by the cooperation of a few ISPs or national intelligence service agencies, which is a realistic attacker model which we learned a few years ago, unfortunately. The other weakness was demonstrated by Biryukov et al. In an attack to de-anonymize large parts of the network. They used the DDoS protection that's run in Bitcoin to blacklist Tor exit nodes, which forced the clients to connect via TCP directly without tunneling through Tor. So they could then just lock their IP address directly. This is another risk of running Tor without any additional mechanisms. A user might not notice when the connection via Tor fails if it's configured to connect without Tor as a default. Also, having a non-private default often leads to people choosing to use the non-private default instead of the privacy-preserving default, minimizing the privacy gains for the group as a whole. One solution that was proposed 3 years ago as applicable directly to Bitcoin is called Dandelion, which proposes a protocol directly implementable in Bitcoin and as a direct protocol as a measure of providing privacy. They add before the spread a privacy phase where a node wishing to disseminate a message spreads their transaction along a line graph throughout the network, and only with some probability, the default is 10%, will at some point the message switch to a regular flood and prune broadcast and spread throughout the network. But this is still quite attackable and only provides some form of statistical privacy for its participants, as a well-connected attacker or many nodes cooperating can easily dismantle most of the privacy provided by the protocol, which is not an attack that is hard to mount and can be created by even smaller research institutes or even single attacker entities. So starting from this, we should evaluate the goals we actually want to reach in such a scenario. As we have a broadcast, we would like to have a protocol that actually specializes in a broadcast. And it should be fast enough for our application and reach every participant in the network. We want sender anonymity. We don't care much about receiver anonymity, which might be a goal in a point-to-point connection. And we would like to have some control over the privacy performance trade-off. The privacy performance trade-off is something inherent in privacy protocols, as we can only gain privacy by trading in some performance. The first point to look at are strong privacy protocols. There are quite a lot. This is just a little selection. Many of them proposed over the last 40 years, some of them rather old, some very new, and most of them don't provide a direct abstraction for broadcast, but can be applied in such a way. But there's one huge downturn to these protocols. They are usually locked to a very high privacy level with very little performance, where we have very little option to actually take control of this trade-off. On the other end of the spectrum, we have these statistical measures, where Dandelion, which I presented before, is one of them. But we would rather be able to move in between these areas of this performance privacy landscape and control this, but also have some strong privacy guarantees if possible. So we presented a concept of this idea at ICDCS 2 years ago, where we used some strong privacy mechanism for a small core of the network, providing some base privacy and building upon this using one of the statistical protocols to provide additional privacy against weaker attacks that can be mounted fairly easily. But to reach all participants in the network, similar to Dandelion, we have a final phase of flood and Bruin broadcast to guarantee delivery within the network. A small recapture, as we will need the information on commitments, which are used heavily throughout privacy protocols and crypto protocols in general. Commitment is some number or information based on some public knowledge. In this case, we have a Peterson commitment. So these are cryptographic keys, G and H, which are public knowledge for everyone and can be seen by everyone. We have a random number R, which is also found here in the index, and the actual thing we want to hide, our secret S. The effect of a commitment given C, we can now provide someone with R and S, and they can validate that the previously given commitment is based on these numbers. But if they only have the commitment, they cannot compute the original values. And also we cannot provide different values that validate with the same commitment. So we are bound to these numbers without anyone knowing these numbers. This is applied in the basic strong cryptography scheme we will use, Dyning Cryptographer Network. The basic idea of the Dyning Cryptographer Network is a fully connected group where only one person wants to send a message in the true original part, and everyone else sets their message to 0. To disguise who the originator is of the message, everyone has to send something. Otherwise, we can just observe who is sending network traffic and detect this person must be the originator. To achieve this, all our participants will send an encrypted form of a 0. so we can reconstruct the original message, but not detect on the network who the originator is. While our sender actually has a message that is not equal to 0, but cannot be seen by anyone else. Also, the other participants will receive the message, but not be able to detect who the originator of the message is. One instance of this protocol from von Ahn et al., which we will look at now as we use it in our protocol directly, works the following. We split our message M in many different secrets, as many as we have participants in our group, and create commitments for all of them. Then we publish our commitments to our values, to our secret shares, but we also transmit our randomness and our secret shares to one to each participant. In this way, each participant can validate that the commitment actually contains what we sent them. Every node does this. So for the second round, before we can start that, we will receive many of these R and S pairs. We accumulate those pairs. We use the XOR here as a combination mechanism, but we could also use addition or other mathematical schemes for that. And we will then publish these aggregated results we received to everyone else. So after the second round, we will receive many of these combined S and combined R values, which we can now combine all together. And in the end, this combined value is a combination of every secret that was created in the beginning. So these that are, if we XOR them all together, equal to the message. So this on the top here is equal to the XOR of all secrets, which is also equal to the XOR of all messages. It's easy to see that if there is only one message, then this message will be the true message and we can decrypt it and read it. We also combine all the R values, so we can combine the commitments if they are homomorphic and validate that everything has gone correct. If there is any error in this, we would have to use a different scheme to detect who the actual problem is, who created the problem, if it was on purpose. These exist, but would be a little bit too much to explain in this presentation. We apply this protocol as a first stage of our protocol, and I'd like to show how we do that. In the first round, we have an array of 2 times the amount of participants of our group, and we have 2 times this amount of slots we will use. Each slot contains one random number, a length, and an array we require for the second phase of commitments. This first phase is basically the exact application of von Ahn's protocol, just that we have a stricter structure on the contents of the actual slots. In the second round, we will now use these slots to create a new array of slots of length L, so all lengths after each other, to actually insert the message we want to send. I'll have an example for this. As I said, the first round is the von Ahn et al. Version, and the second round, which we use as an additional dynamic cryptography round, is our addition to this protocol. As a simple example, if we have 3 participants that want to send some messages, they select one slot at random and then create the XOR of all of those slots through a dynamic cryptographers round, which we can now see here. And given this, they will create a new Dining Cryptographers round and fill in their original slot, which they can identify via the random number and the length, and set everything else to 0. Our third participant would just use a complete 0 string as their message. The XOR of all these messages again will lead all the previous messages just appended to each other, where we still know the borders of the messages thanks to the length we had in the original message. After we have now shared our message securely in our small group, we would like to share it in a reasonably safe way throughout a larger part of the network. For this, we decided to use the Adaptive Diffusion protocol by Fanti et al., which in the first step, the responsible person to disseminate the message will select one neighbor at random and give them the responsibility to start the actual diffusion of the message. This person is now responsible to create a tree-like structure where it seems like they are the center of the message, which is equivalent to seeming like the originator if it were an actual flood and prune message. To show this a little bit more easy, we will add this small tree rewrite of the current structure. Our new node selects two neighbors in this instance. This is a parameter we can use later where they will disseminate the message to. So now we have this little structure where our orange node is the apparent center of this tree and the apparent originator of the message. In the next round, the apparent center can now decide to either increase the size of this tree, which it will do now, or find someone new to be the apparent center. Otherwise, we could always be sure that the true originator is a neighbor of the apparent center. We decided to reduce this threat as a new parameter, as selecting all possible neighbors is again a possible leak for privacy. When we decide to find a new center, the node will select one of the neighbors that participates in the protocol and give them a little bit of extra information so they can balance the new tree. We will clone this one and rearrange it a little bit. We can see that it's the same tree as before, just rearranged so that the green node is now the apparent center. So the green node has to spread the message on the left branch of this tree. Obviously, there can be interconnections that complicate the setup a bit, but the apparent center will still seem to be the green node. If we take this and just assume that every node in our red block down here is an attacker node, and we can now detect all of those nodes, detect they received the message right now, and they know the topology of the network, they can now compute the apparent form of this tree, or the smallest version, and detect and just compute the apparent center of this tree. This technique smooths the probability of one node being the originator. A node in the center is only slightly more, has a slightly higher probability only being the true originator than a node closer to the edge. In this case, it's very likely that it's not one on this side, as these nodes would actually receive the message earlier due to the transmit over here. This protocol has one large drawback, as it has no termination detection. So we have to define a number of steps for which we want to run this protocol. This depends on our parameters and the size of the network, but at some point we want to stop, and there's no guarantee we reached all participants in the network. To change this, we just add a flood and prune phase to the broadcast, so the last apparent center just switches to a flood and prune, which will reach every node in the network. Given this protocol, we now have various parameters that we can look at and we can evaluate for our system. On the network side, we have the size of the network and the connectivity, so how many connections does every node in the network actually have. For our DC network, we have the group size as one major parameter, and on the diffusion we have the depth, so how many steps do we actually take, and we have the spread parameter, so how many neighbors do we select. To get an evaluation of these parameters, at first we looked at the bandwidth of the system, as this is the major limiting factor of dynamic cryptography networks. We can see that we have some k-square values over here, which is not optimal, and the main reason that dynamic cryptography networks usually only scale up to 40 or 30 participants. But as a base privacy measure, these are in the estimates usually, or the recommended values usually set by a privacy expert for these kind of anonymity schemes. One bad thing about this, we can see the values of 32 everywhere in this system. These are basically dependent on the cryptographic scheme used for the commitments. And the first message, these are based on the randomness values, the array we added before. And in the commitments, those are the actual sizes of the commitments. These are the largest contributors to the actual size. As we can see, here is one of the squares case. The good thing is we can run our protocol in a less secure way until actual malicious problems are detected, as we can notice when the messages are unreadable at the end of an instance. And we can turn off the security properties of the protocol and turn them on once such a problem is detected. So we can remove many of the expensive phases and reduce the bandwidth. In the secure way, we easily go in the low megabytes of transmission per message or per multi-message transmitted. So we would like to remove those in the happy pathway, so only apply them and reduce a lot of the bandwidth. To estimate the latency implications of our protocol, we built a simulation of the system. This is one example run of a small network to display the problems, where we can see the phases of our system in different colors, and we use this to log all the message transmissions within the network to measure the latency of the phases and protocols. We also implemented other similar protocols and baseline protocols, flood and prune as a comparison, so how long would it take if we used the baseline protocol, adaptive diffusion, which we used as a phase, and Dandelion, which is a competitor protocol. For the slowdown of Bitcoin, you would see the latency somewhere out of screen here. As I said, they basically have an average of 5 seconds with a maximum of 30 seconds, which is far above the actual results for most of our protocols. The only outlier is Dandelion. As I said before, Dandelion switches its phase with a base probability of 10%. So there's a low probability that it will take very, very long for some runs. And here we display the median of the runtime in red and the 99th and 99.9th percentile of the runtime in green and blue. And the probabilistic approach of Dandelion has the negative effect that the 99th percentile is exactly this very low chance of getting off the charts, and it will end up somewhere above here, similar to Bitcoin. We also analyzed the the basic parameters of our system and their impact on latency, but we came to the conclusion that most have little impact on latency and are most likely bound by the bandwidth of the system, as we already knew before, suspected beforehand at least. The most interesting parameter is the newly introduced spread, so how many neighbors does our adaptive diffusion variant select. And selecting fewer neighbors, the lower end of this graph, of this box chart, obviously is preferable for privacy, but the higher end is probably preferable to reach more nodes easily. The red crosses around here are the outliers of the system, while the rest shows the distribution of the measured values for all things. But there's a clear trend for the median values, which holds for statistic significancy tests, which we performed. So there is a clear improvement in reaching most of the half of the network faster. So we measured how long does it take to reach half of the network using this protocol. And it is faster with more more neighbors selected, but it is not that much faster that it is worth to sacrifice the privacy usually. Unfortunately, there is a last weakness due to the application with blockchains, and that is we still have this public ledger of all transactions, which can be used to cross calculate and cross de-anonymize participants, and this weakens the actual effect of the privacy parameters. We can see here the transaction anonymity, which is the ring signatures I mentioned before on the blockchain itself, and their variability, as well as the size of the DC network. And we can see that the DC network has a strong impact at the overall privacy, but the de-anonymization through the transaction information added to the computation is significant. So even with reasonable parameters, we will get reasonable privacy, but we usually have a reduced privacy set in the end. So the privacy is reduced for most participants through the system, so we cannot compare it to applications outside of blockchain space where we don't have this overall information. While these results stem from a simulation and not a real implementation of the protocol, a real implementation is in the works and it's finished. We started the evaluation stage of the protocol. Unfortunately, we don't have any preliminary results yet for the protocol, besides some initial test runs which suggest that our results from our simulation are valid and not too far off from the expected results. Besides this, we worked on some I worked on some improvements on related issues to this protocol. In the beginning, I explained the basic idea of the DC network, and there's one major problem with DC networks, and this is jamming of the message. As nodes are required to set their message to 0, we can have malicious nodes that set their message to random values. Initially, this leads to not being able to disseminate valid messages. Unfortunately, the jamming node also can reconstruct the original message, as they can compute the difference between their random value they can remember and the shared message, and then retrieve the original message. This is not easily detectable by all participants without additional measures. In the original protocol, it is only detectable by the original sender. Modern versions of the DC protocol have additional detection mechanisms. Some of them use the aforementioned commitments before to isolate the node that performed the jamming, but it does not prevent the attack for the first round, where the node can still read the message that is supposed to be disseminated. This can lead to problems in some instances, especially, for example, in blockchains where a node reading the message could do some front running. We worked on a solution to this, and the core idea is splitting the message using a secret sharing scheme, where in the end multiple parties have to combine their results to then compute the original message. This increases the cost for an attacker, as they need multiple nodes inside our group. And if they can't do that, we also even prevent the attack from occurring or from succeeding in any meaningful way. For this, we used Shamir secret sharing, which basically conceptually sets the message as the 0th point of some polynomial, and then shares other points of this polynomial where the degree of the polynomial is known with other participants. For example, if we have a polynomial of degree 1, 2 of our participants could cooperate and recreate the message. In our application, let's assume we have 4 participants. Every participant would create such a polynomial for their message, where most of the original points are 0, and would send them to every other participant. So our first node creates f1, the polynomial and the points, and shares them, and receives the first point of all other polynomials. We can now see that using the original protocol, we basically receive the XOR of all polynomial shares. And we would now like to reconstruct the original message from this XOR of shared points. Luckily, as long as we operate over the Galois field of base size 2, the XOR of our messages is equivalent to the sum of our messages. And the sum of polynomials in this field also contain the 0 point. So the sum of the 0 point is the sum of the polynomials. So even though we have a sum of polynomials, we still can reconstruct the original 0 point message as long as the other messages are 0. And we have enough cooperating members. With this, it's much harder for a malicious entity to actually compromise a network and read a message while jamming. To further improve this, we would need to reduce the chance of having multiple entities in the network cooperating. And for this, we looked into the group creation scheme to actually build our DC network groups. Originally, if we have some group, there might be some nodes that cooperate in some way. There might be some nodes that are from Google, which just want to work in the network as a whole. But we would prefer it if only one computer from Google participates. There might be multiple nodes from a botnet, or some script kiddie having multiple nodes simulated on the notebook at home, or some researcher trying to collect some privacy data. And the basic scheme we came up with is a two-phase scheme. In phase 1, we create a preliminary group At first, we can use an IP filter and previously established trust information, like have we worked with this person before? Do we know them from some other context? Something like that. And this allows us to specify that we would like only one participant of Google, please. Once we have such a preliminary group, we switch to a modular new protocol, and our two base modules are memory testing and a CAPTCHA for various reasons. The first we discuss is the CAPTCHA that allows us to make increased cost for botnet participants. It's still solvable as there are CAPTCHA solving services, but they're much more expensive than not having them. And the script kiddie, which basically could solve two CAPTCHAs quickly enough, but cannot simulate having actually two memory buses usually. So a memory testing algorithm will lead to exclusion for this. If this succeeds, we can create a full group, and if this does not succeed, we will cancel the group creation and find new participants. But we will also use this information we collected as trust information for the future. Unfortunately, for this scheme, there are many limitations and challenges we are still facing. On the one hand, this scheme is obviously still attackable, so it can still be broken. For all steps, there's something something you can do to break it. It just increases the cost in various situations and is not more easily attacked than the status quo. On the other hand, the challenges we are facing, the quantification of the privacy we could gain through this system, is very hard to quantify. And the evaluation turned out to be very challenging to produce some meaningful evaluation for such a scheme. So let's come closer to the end. As a summary of this talk, we saw there is some privacy problem in the dissemination of transactions for blockchain systems. When the transactions are disseminated in the network, there might be attackers listening in. We presented a protocol that can solve this problem in a way by providing a strong base privacy, so we can still have reasonable performance, but also adding some statistical privacy methodology so we can have additional privacy against common attackers. We saw how the system works, and we also showed in our publication that it provides privacy in a beneficial way. While we're still working on a real-world evaluation, we already showed a preliminary evaluation of the properties of our system, so we have this well covered. Outside of this, in the surrounding setting of our system, we saw that we can improve jamming message reading resistance of the system by using secret sharing in our protocol. We can improve group creation of our system, and besides that, we also provided some additional measurements in Bitcoin for the problem analyzation and transaction measurements within Bitcoin especially. But this would, in the end, provide too large for this talk. As a finisher, I would like to show our already published works on the related topics, as well as a short discussion of planned and pending publications. We're mostly working on the protocol publications on the top left, which are the evaluation and stricter specification of our protocol, as well as the only mentioned measurements and estimation within the Bitcoin network, and the limitations of group-based privacy in blockchain systems with public ledgers, as well as the improvements I mentioned for the threshold cryptography scheme, the group creation, and some related network formation schemes that even help create more efficient networks that contain such groups or make it easier to specify the parameters required for our protocol. There are also some unrelated publications in the IoT world, which I will skip now. Thank you very much